Thank you for your attention. I'm very thrilled to introduce Dr. Anne-Marie Madigan. She's currently at UC Berkeley, where she is an Einstein postdoctoral fellow. She has her PhD from Leiden University and her Bachelor of Science in the Physics and Astronomy program from the University of Galway, or the National University in Galway, Ireland, which you may notice from her accent here today. She studies stellar dynamics near massive black holes. And so this is related to some of our courses in the fall, a wonderful research topic, and one that I think we can see has brought people out because of the concept of black holes and extremely large black holes. So let's put our hands together and welcome Dr. Madigan.
Okay, thank you very much, and thank you so much for inviting me here. It's a real pleasure. I'm going to be talking today about the center of our galaxy. And zooming out first, I'm putting this image up because this is what our galaxy would look like if we could observe it from outside the galaxy. And we, and our solar system, would be located on one of the spiral arms quite far away from the galactic center. If we're going to zoom into the center, I've got a schematic here of what we would see. That's a supermassive black hole in the center, and a cluster of stars that are on elliptical orbits around the massive black hole, much like planets are on elliptical orbits around the sun. But we're about 24,000 light years away from the center of our galaxy, and it's very difficult to observe. So I want to answer the question why we bother studying the center of the galaxy at all. There are many other things we could study. Personally, there's exoplanets, cosmology, large-scale structure, galaxy formation, so many interesting topics in astronomy. So why do we do something that's very difficult? This is an image in optical, it's a photograph, of the galactic plane. So we're on the outskirts of a galaxy looking towards the center. So we're looking straight into the galactic plane where most of the matter is. So that's not just only stars, there's a lot of gas and dust intervening, and you can see it forms a cloudy distribution blocking our sight into the galactic center. So we actually cannot view the galactic center in optical because that intervening dust and gas absorbs a lot of that light and scatters a lot of that light. So we have to look at different wavelengths, in particular infrared, hard X-rays, gamma rays, things like that. But why do we do that? So I have two personal reasons. I hope you can see down there. Is that blocked? Okay. The first is the sheer density of exotic objects in the galactic center. And I'll begin my talk on this because it's really quite phenomenal. And the second reason I study the galactic center as a theorist is because the dynamics is so beautiful. It's very simple in some ways. Stars move around a massive black hole. Like I said, planets move around the sun. But their interactions between each other can cause really amazing, complex dynamics. And it can cause stars to actually interact with the supermassive black hole in the center and produce some of the most energetic phenomena we see in the universe. So the structure of my talk is going to be separated roughly in these two parts, looking at the density of objects we have in the galactic center, show some observations of the galactic center, and then compare that to the predictions that were made before we were able to take these observations. And we'll see that there's a huge discrepancy between predictions and the observations. And then I'll move on to the second part of the talk, which is about dynamics, and how understanding the dynamics of objects around the massive black hole can help us resolve those discrepancies. So, to give you an idea of the density of the volume around the galactic center, I'm going to first compare it to the solar system. So I'm going to pick the center of the sun, and I'm going to draw a radius of a parsec out. And so a parsec is roughly 3 light years. And then I'm going to look at everything that's contained within that volume and see how much mass there is there. So the first thing to say is that within this particular volume, we believe the sun is the only stellar object. Our nearest observed star is Proxima Centauri, and that's about 4.3 light years away. So within this volume, the sun is king or queen. What we do know, of course, is that we have all the major planets and also the minor planets. So we've got Saturn and Earth, and of the planets, Jupiter is the most massive, but it's still far less massive than our sun, maybe 1,000th of a solar mass. Nothing is to scale here, obviously. We've also got comets, we've got asteroids, and we've got evidence of an Oort cloud further out. This distribution of material that can sometimes be set straight into the center of the system and interact, unfortunately sometimes, with the Earth, killing dinosaurs and things like this. We also have comets, which you can see up here, and these icy bodies that we see in particular when they pass close to the sun. But that's pretty much it for this volume of space. And overall, we can say in 1 parsec cubed, we have pretty much 1 solar mass. And that would give us the density. So I'm now going to compare that to the center of our galaxy. So the first point of contrast is that in the center of our galaxy, instead of the sun, if we look at the exact geometric center, we have a supermassive black hole. And that's 4 million solar masses, or 4 million times the mass of the sun. So that's already a huge change. Again, we're going to draw a volume around this object and ask what else is in that volume. So the first thing to say is that there's a nuclear star cluster. So this is a star cluster that contains all different types of stars, of which we can only actually observe the most luminous, typically in infrared. But the mass in stars is quite phenomenal. In this particular volume, we think it's another few million solar masses of stars. So it's pretty spectacular. We observe the hottest, brightest stars. We also observe red giant stars that are colder but more luminous because they've got such an expanded envelope. But we would theoretically predict also stars that we can't see, including stellar remnants, so white dwarfs, neutron stars, and stellar mass black holes that are much harder to see. Recently, we discovered an object, which I'm depicting here, which is called a magnetar. And a magnetar is a highly magnetized pulsar. A pulsar is a rapidly rotating neutron star. And to give you a sense of just how extreme this object is, if I can remember the numbers now, I think on Earth, the magnetic field measured in Tesla is 1/20,000 of a Tesla. Okay, good, I see some nods, I've got it right. If you try to generate a much higher magnetic field on Earth, you can do so in the laboratory, but building up a lot of magnetic field strength in some materials, in all materials, creates magnetic pressure, so you're in danger of blowing up your lab. And this has happened. So I think the maximum strength you can reach without blowing up your lab is 100 Tesla. This object is 1 billion Tesla in strength. So it's pretty amazing. Oh, another funny fact I learned when I was researching this for this talk. To levitate a frog off the Earth's gravitational field, you need 16 Tesla. I just wanted to add that in. So in contrast to our solar neighborhood, the gas density, well, maybe not the density, but the gas temperature in the galactic center is extreme. It's about 10 to the 8 Kelvin. So this room temperature is about 300 Kelvin in comparison. So this is X-ray emitting gas that everything is flying through. So it's pretty extreme. It doesn't contribute much to the mass budget, but it gives you an idea of just how incredible this region is. And the last thing, oh yes, so I wanted to summarize by saying there's about 10 million solar masses in this volume of space compared to 1 solar mass in our solar neighborhood. So it's pretty amazing. And the last thing I wanted to mention, because I'll get back to this at the beginning of my talk, again, it's not important for the mass budget in this volume of space, but it's a really interesting object that we're observing right now. This is a gas cloud, apparently a gas cloud. It could still be a star, we're not totally sure, called G2. And it was discovered because it is hurtling towards the massive black hole at thousands of kilometers per second and should be ripped apart and be fed into the black hole. And this is really unusual in astronomy, to find something that's happening in real time that we think we understand, and then can make this experiment of what happens when you throw a gas cloud directly at a black hole right now. So all the telescopes in the world, well, not all the telescopes that can look at the galactic center to get meaningful measurements over the past couple of years have been pointing at the galactic center. And that's actually how we discovered the magnetar. So we're all looking at G2. Okay, so this is a schematic picture. So I wanted to give you some idea of what their observations actually look like. So this is actually a much larger picture. This is from Spitzer Space Telescope looking at infrared. And the galactic center is actually located here in this bright spot. So we're just going to flick through some images. This is Spitzer, infrared, and it's picking up a lot of gas and dust that's being heated from stars. And it's also actually all these little pinpoints are individual stars that we wouldn't be able to see in the optical. So they all shine very brightly in this wavelength. This is the exact same image with the Hubble Space Telescope, again in infrared. You can see there's some really interesting structure going on in the galactic center. This is also gas and dust that's being illuminated by massive stars. You can see some really strange arcs happening out over here. This is what it looks like with Chandra X-ray Observatory. So the pink colors is slightly less energetic X-rays. The blue are extremely energetic X-rays. And you can see the galactic center is clearly outshining everything else in this image. So this is the composite image when they all get put together, and I think it's really gorgeous. But it shows, again, that the galactic center region is extremely energetic. There are X-ray photons being emitted, possibly from an outflow from the massive black hole, definitely from colliding stellar winds from giant stars. And also there are point sources, many hundreds of point sources in this region that are thought to be X-ray binaries, so binaries that contain either a stellar mass black hole or a neutron star, and they're accreting matter. So very interesting region. So now I'm going to focus on just the smaller part of this, the galactic center region, and about a parsec cubed volume. And I want to ask, you don't have to shout out, but what would you expect for the distribution of stars in this region? You might expect, because it's the center of the potential of the galaxy, there would be many stars, and I've already told you there are. But what would you think they'd be doing? Would they be very old, very young stars? Would they be distributed in a certain way around the black hole? So what the predictions are is that you would expect old stars to be distributed in a very strong and steep density cusp going towards the black hole, so increasing in density as you get towards the massive black hole. And that's true in gravitational interactions between the stars losing energy, moving inwards. So there are three theoretical predictions from the 70s saying this is really what you should be seeing. We can't see all the old stars in the galactic center because they're not that luminous, but we can see a proportion of them. For example, red giants, which I mentioned before. So if we look at the red giant population, we expect to see them increasing in density as you get close to the black hole. Another strong prediction is that you wouldn't expect to see any young stars. And the reason for this is that you form stars from collapsing molecular clouds. They fragment and collapse under their own gravity as they're radiating away their heat. But the problem is, we see this elsewhere in the galaxy. We look at molecular clouds and you can see evidence for star formation in these clouds. But if you were to take that same molecular cloud and put it beside a supermassive black hole, it would be ripped apart because the tidal forces acting on the side closest to the black hole are so much stronger than the forces acting on the side away from the black hole. So it would just be completely stretched out. It wouldn't have time to radiate away its heat and collapse and form a star. So yes, you would expect old stars to be drifting inwards, but young stars, they don't have that much time because by definition they're young, so you wouldn't see very many near the black hole. And this is what the galactic center looks like when you zoom in to the central parsec region. So this is actually taken with the VLT in Chile using adaptive optics. And these are infrared colors of stars. And the redder stars, these are red giants. These are the stars that you would expect to find. In the center of the image is the black hole, but you can't see it because it's a black hole. The blue and white stars are young stars, very young stars. And you might see already, just from this image, knowing nothing about the kinematics or where they are in space relative to each other. We have no information here on the spatial dimension. You can see there are many more young stars than old stars. So there's something quite strange happening here. So what people have done is take that type of image repeatedly, year after year, for almost 2 decades now. And of course, instrumentation is improving, so they're getting better and better at this. And then you have this snapshot in time of the positions of all the stars. And then you can actually follow the stars from frame to frame until you find that they're orbiting a massive black hole. And this is actually how you find out the mass of the black hole in the center. Because of course, just like Kepler's laws in our planetary system, if there was no sun at the center, all the planets would just fly away. The reason the Earth travels at the speed it does, at the distance it is just because of the mass of the sun. So you can do that same experiment in the center of the galaxy, and you find out the mass of the black hole from all these different stellar orbits, and it all adds up to 4 million solar masses. So I'm going to show a movie of reconstructed stellar orbits from all of this data, from the UCLA group, headed by Andrea Ghez, and this is also by Silvana Yelda. So we start zoomed in a little bit, and they've color-coded the stars. The green ones are very young stars. The old ones are orange stars, and I think magenta are the ones that still aren't confirmed which ones they are. So you were zooming out from the center. You can see at this point the stellar orbits are oriented quite randomly with respect to one another. They don't seem to have a very defined shape. They're all quite eccentric. None of them are particularly circular. But as you zoom further and further out, you can see that many of the young stars, they're all the green stars, are orbiting in a disk. So this was a real surprise, and this is not theoretically predicted, but it was recovered from the data after many years. You can also see, again, in this image, the sheer amount of green stars that you wouldn't have expected. You don't expect these young stars to be forming there, and relatively very few orange stars or old stars. And of course, there are many more stars, but these are the stars we have orbits for to find the best. So, how did the young stars actually get to be there? Well, it turns out, since we do see the stars there, we have to look a bit harder at how you form stars near a massive black hole. And indeed, if you throw a molecular cloud straight at the black hole, it can be ripped apart, you're not forming stars. But if you can get the cloud to form an accretion disk around the massive black hole, that density within the accretion disk can actually overcome the tidal forces. And far away from the black hole, not right beside it because it's going to be way too hot, that gas that's too close to the black hole, but far enough away, you can get these clumps fragment and start forming stars further out. So that can explain that disk of stars that we saw in the previous movie. The problem is we also see stars that are really, really close to the black hole, within the inner edge of that disk. And you saw all the orbits were randomized, they didn't look to be on a plane. So where do they come from? Just showing an image. These are typically called the S stars. And I'm showing an image, snapshots, stacked on top of one another, where these stars are moving around on their orbits and not aligned in a plane. So this is still a mystery. How did we get the stars in the inner edge of the disk to where they are today? And they're not particularly circular. They're extremely highly eccentric, in fact. And as I said, they're not aligned with the disk. So this is to summarize the conundrums and the paradoxes, as they're called at the moment. The first is the red giants, which I haven't addressed yet. This is called the conundrum of old age. Where are all the red giants close to the black hole? So you see we have a few, but if you look in if you try and reconstruct the orbits in 3 dimensions, it seems actually there's a hole in the distribution of red giants around the black hole. So they increase in density up till a point, and then they actually invert in their density profile. So for some reason, those red giant stars have just been excavated away. And the second problem is this paradox of youth. So if we accept now that we can theoretically form stars in a disk around a massive black hole, and that's how we formed a lot of those young stars we see in the galactic center, what about the young stars that are even closer to the black hole, that are not on the plane of a disk and have very highly eccentric orbits? So what's going on with them? So I want to move now to the second part of my talk, and at the end I'll be getting back to those questions. So I want to talk about the dynamics of stars near supermassive black holes. And I said the orbit of a star around a massive black hole is, of course, very similar to the orbit of a planet that's around a star. It's the same type of potential, gravitational potential. So it's been studied for hundreds of years in celestial mechanics. And you can say that the orbit of the star is defined by its energy and its angular momentum. The energy is related to the semi-major axis of the orbit. So that's the mean distance that the star orbits around the massive black hole. And its angular momentum is related to its eccentricity, or just how circular an orbit is, or just how radial the orbit is. So if the star only felt the force from the supermassive black hole, it would have the same semi-major axis and eccentricity for all time. It would repeat the same orbit again and again. After it repeats an orbit, it lands back in exactly the same place, just like the Earth lands pretty much back in exactly the same place. We're not doing some strange orbit year after year. But in the galactic center, there are so many other stars that that's not the only gravitational force the star will feel. It will also feel those forces from the other stars that are extremely nearby. And they'll be subdominant. So you can still describe the orbit in this way, but those forces are still going to be changing these properties, semi-major axis and eccentricity, on relatively fast timescales. So what does that do? So I said this, the stars change their semi-major axes and their eccentricities through gravitational interactions. We call this process relaxation. And that's because if you start a distribution of stars off in a strange manner, I don't know, all aligned in a disk or something with a lot of structure, you would expect over a time scale, through gravitational interactions, that the system relaxes into some minimum energy state, some equilibrium configuration. So that's why it's called gravitational relaxation. And typically, in gravitational relaxation, you expect the dominant mechanism to be called something called two-body interactions, or two-body relaxation, where you have a star and another star. They come slightly close to each other. They gravitationally accelerate each other and very slightly change their energy and angular momenta, or semi-major axis and eccentricities. And you can add up all those interactions a star can have, and you can say, okay, over some time scale, through these little small interactions, orbit changes very slightly. But it turns out that this is not the dominant mechanism of relaxation near a supermassive black hole, because as you see, a star is orbiting the same orbit again and again and again over long time scales. So it's not the case that a star interacts with one star and moves away, and then in another million years comes close to another star and does something different. These gravitational interactions build up over orbit. So I don't know if this is going to help at all. But you have the same interaction, you move away, you have the exact same interaction, you move away. So it's coherent interactions. And if one interaction changes your eccentricity to make you more eccentric or more circular, the next time you orbit and pass close, you're doing exactly the same thing. So you go very fast in either direction in the way you change. One way to think about this, I should say, this is called resonant relaxation. It's a fairly new concept in this field, although it was already known in planetary dynamics. One way to think about this, to make it more intuitive, is to no longer think about stars as individual point particles that may interact with each other incoherently, but to spread the mass of the star out along its orbit. And you make the density at a particular part of the orbit inversely proportional to the velocity it has at that point. So you end up with a system of massive wires that are very heavy where they're the slowest, And then these massive wires, they feel gravitational forces that actually gravitationally torque each other's orbits, just like a normal torque on Earth. And this torque, turns out it's the rate of change of angular momentum. So this changes the eccentricities really fast. So that's a way to think about it. Massive elliptical wires and their eccentricities are changing rapidly because they're around this massive black hole. So as far as I know, there's no other place in the galaxy that this is so efficient, other than planetary systems on a much smaller scale. So stars change their eccentricities very fast. And why is that interesting at all? To somebody who doesn't study dynamics, that might not seem very glamorous. But supermassive black holes have a tidal disruption radius, like any object. And this is defined differently for different objects. It depends on the density of an object that's orbiting the massive black hole. But if you have a star, a gas cloud, anything that has some density, there will be a radius beyond which, if it passes, the tidal forces acting on its sides are going to unbind the object. So if this is a star, it's basically you pass through a certain radius, and the star will actually be ripped apart because the gravitational force holding the star together can't compete with the tidal force of the black hole. And this is going to happen for gas clouds and all different types of objects. So the radius will change depending on how dilute you are or how concentrated you are as an object. So if you have a tidal radius around the supermassive black hole in the galactic center, this means that if you have a star, this is here, a little star, on an orbit around the black hole, if it gets more eccentric, it's in danger at its position of closest approach of entering the tidal disruption radius. And what happens is there will be an eccentricity for any given semi-major axis that if you get beyond that eccentricity, you enter the tidal disruption radius and you do get ripped apart. And this doesn't happen all the time, so we don't see this right now in our galactic center, but we do see evidence for this in other galactic centers. It produces a huge burst in radiation. And this is an artist's impression of the fact that a star getting close to the black hole, entering the tidal disruption radius, about half the material, classically, so not involving general relativity or anything, half the material will get flung out at really high velocities, and the other half of the material will remain bound to the massive black hole and eventually get consumed. And it's this stage of the process that's extremely luminous, we think. But this does not only happen to single stars. This can also happen to stars that are in binary systems. And this is called the binary disruption mechanism. I apologize for the extremely childish cartoon, but basically this is where you have a binary system that's orbiting the supermassive black hole, and it has a tidal disruption radius that's going to be larger than the one for a single star. But this radius, if you enter it, unbinds the binary system. So not ripping apart the individual stars, but actually ripping apart the binary itself. And what happens in that case is one star, like 50% of the system, is flung out at really high velocities. It can even form a hypervelocity star. We actually see them in the galactic halo. They're escaping the galaxy. And as far as I know, this is the only known mechanism that can actually generate sufficient velocities that you overcome the escape velocity of the galaxy, if you're starting from the center. The remaining star, just like the single star forming an accretion disk, it remains bound to the black hole, but it's still intact. It's still a star. And what you would observe with these stars is that their semi-major axes are, now if you plug in the numbers, this is mass of the black hole, mass of the binary system, and then the semi-major axis of the binary, the innermost binary. If you put in those numbers, you actually get extremely close to the black hole, these semi-major axes, and extremely eccentric orbits. So if this is happening in our galaxy, you would expect to see not only hypervelocity stars, which we do see, but you'd also expect to see a population of stars very close to the black hole on very highly eccentric orbits, which we see. So this is most likely the red giants, to start with. there are many different ideas of what's happening to red giants, why we see this hole in this late type population of stars. And one idea that I've had and I've written about is that maybe this process, beside the supermassive black hole, that you're pumping stars onto highly eccentric orbits and they get tidally disrupted, this is happening for the red giant population. And it makes sense because they're old, and this process of pumping stars onto highly eccentric orbits, just due to gravitational interactions between other stars, that takes a long time. So you would expect to see this hole in old stars, not young stars. And red giants are also very extended objects, so their tidal disruption radii are much larger than it would be if they were compact. So this should happen more easily for red giant stars than any other type of stars. So this is a possible explanation. But I should say it's not the only explanation. There are other ones, such as stellar mass black holes that we theoretically expect to be near the massive black hole. Black holes everywhere. They can rip through red giants. It can collide directly with the red giants. And if you have a sufficient number of these collisions, you can actually totally destroy the red giant star. So this is another idea, that all the red giants in the galactic center, very close to the black hole, have actually had so many collisions with stellar mass black holes that we no longer see them. So it's pretty exotic theories, but we need that to explain what's going on. The second paradox that we had, the paradox of youth, what's going on with stars that are closer to the black hole than you can theoretically produce from an accretion disk? Well, the idea there is that perhaps the stars in the disk, these young stars in the disk, are getting pumped up to high eccentricities, and this binary disruption mechanism is taking place. So if you form binary stars in the disk, and we don't know if we can, but if you can form binary stars in the disk, as they get up more eccentric, they don't have to come as close to the black hole to enter the tidal disruption radius that breaks the binary apart. So this would form stars, get stars from the disk, get them close to the massive black hole on highly eccentric orbits, and we do see them on highly eccentric orbits, and their companions would be flung off into the galaxy, which we see. So this is a mechanism that could work. Unfortunately, it doesn't work perfectly either. So one problem is that disk is about 4 to 6 million years old, and the stars very close to the massive black hole, it's very hard to constrain their ages, but they could be between 4 to 6 million years old and 100 million years old, still very young. But if they are 100 million years old, they couldn't have come from this disk. So it's not totally clear if we've solved the problem. But dynamics can definitely help with both of these. And there are many more mysteries going on in the galactic center. And I want to end my talk talking not about stars, but about this possible gas cloud that's in the process of being ripped apart by the black hole. So this gas cloud is called G2, and I've got an image here. This is it. It might not look so dramatic. And this is the stream of gas that's trailing behind it. For the galactic center, these are really amazing images, though. So this is a red, dusty object that has some gas associated with it. And it was discovered in images because it's traveling thousands of kilometers per second towards the black hole. I've been tracking it now very closely for the past few years, 2 years to be precise. And it's already hit periaps position. So that's a position of closest approach to the massive black hole. And we can see in gas, it is tidally extended. So the gas component of this object is very much interacting with the black hole and should be totally disrupted and accrete onto the black hole. We should see the black hole feeding. It's on a very highly eccentric orbit, and we don't know exactly why that is. And the gas cloud idea is actually not the only idea for what this object is. People like to think that maybe there's a star in the middle of this object, but it has to be very faint, because this is K-band emission, this is L. We don't see it in K, which basically, for the purposes of this talk, means it's not a typical star in the galactic center. So if there is a star in the middle of this object, it has to be very faint, and then it's not clear why there's this dust and gas associated with it. So the best stellar hypothesis that we have right now is not that it's a normal star at all. It would be the merger of two stars that we just happen to have caught just after it merged. So there's still a lot of gas and dust associated with this thing. So either way, yeah. Oh.
Dr. Madigan, can you show us where the center of the galaxy is? Is it in that image? Is it?
Yes, it should be. Again, you can't see it.
Yes.
Yeah. Let's say it's around here, if that's any help. So you can see its orbit kind of traces around here.
And about what percentage of this, if it's a gas cloud, is in the sort of nuclear gas cloud, the one where the arrow is pointing to, and how much is trailing? Can they? So the estimates on the mass for G2, which is this particular blob, is about 3 Earth masses. So not a lot, not very massive whatsoever, and should be entirely destroyed. I don't think we have estimates, or I don't know them off the top of my head, for what that trailing stream has, less than that. But I think one of the most interesting things about this object is not just that there's a single object, but there is a G1. There are many objects like this. G2 just happens to stand out because it was traveling so fast, and we realized it's going towards Perry-Center this year. There are many other objects, such as G1, ones that don't have denominations yet. We're not sure what we're going to call them. So if they're gas clouds, this is very interesting. We're very interested to know how a gas cloud gets fed to a black hole. We can test a lot of theory of accretion disks and things like that. If it's a merger of two stars, that means there are merger products all over the galactic center. Stars are just merging left, right, and center, which is fantastic. It's very interesting. Yeah, so we have to stay tuned, though, and see what the observations show us. Right now, I'm working on simulations of a gas cloud plunging through this X-ray emitting gas around the massive black hole to see what type of, what constraints we can put on the gas around the black hole from these observations. And I want to finish with a movie. Are you
able to figure out anything about the density of G2 from the infrared observations?
Yes. Well, it's okay. Maybe not from the dust, but from bracket gamma emission. So there's dust and gas associated with it. So the gas, the gas is at 10 to the 4. You are. But I'll think how best to answer that. Yes, and I guess from the density that you get, you can calculate a mass. So they do have that. So I wanted to end on this movie from the European Southern Observatory. This is a hydrodynamic simulation showing again reconstructed orbits of stars around the black hole, but also, like we're going to hit the present day at any moment now, also showing what the G2 gas cloud should be up to if there is no star in the center, and what we could look forward to in future decades with observations. And the scale here is 10 light days. And in the meantime, we'll have the 30-meter telescope, things like this. So everything is just going to get better and more interesting. And hopefully we'll figure out some of the mysteries. So to summarize, I think I've finished quite early. In the galactic center, there's a lack of old stars, in particular red giants. It's not clear if red giants trace the rest of the old stellar population. Maybe this is something just to do with red giants and all the old stars that we cannot see because they're not luminous enough, like white dwarfs, neutron stars, stellar mass black holes, are still there. Or if the red giants are really telling us something about there being very few old stars around the massive black hole. And that has repercussions for tidal disruption event rates, for gravitational wave emission events. When you have a stellar mass black hole that inspirals into a massive black hole emitting gravitational waves, if there are no stellar mass black holes around the galactic center, or around the black hole, that's a problem, particularly if we want to fund observatories that look for these gravitational wave emission events. There's an abundance of young stars. The galactic center is one of the most star-bursting regions of our galaxy. We now think that you can form stars around a massive black hole in an accretion disk. And we do think that stars closer inwards, called the S stars, are coming from a binary disruption mechanism, which explains both their presence in highly eccentric orbits and the hypervelocity stars we see in the galactic halo. G2, in the next couple of years, we'll figure out whether or not it's a gas cloud or perhaps it's a star or a merger of two stars. But either way, it's a very interesting object, and there are many more. So I think new physics is going to come out of this. In the dynamics part of my talk, I talked how stars, if you can consider their mass spread out along their orbits, they're gravitationally torquing each other. And this is a much more efficient mechanism than elsewhere in the galaxy, so they change each other's orbits rapidly. And this can cause tidal disruptions of single stars onto the massive black hole, and also the binary disruption. And I'll stop there. Thanks.
We have good time for questions for Dr. Madigan. Yes, let's start with Tom.
Based on the hydrodynamical simulation and the gas streaming off of G2 onto the accreting around the black hole, what kind of luminosity would you expect from the accretion disk? How bright will this get based on the new feed of gas from that simulation?
That's a good question. I don't think it's going to be an extremely luminous event. There's not a lot of mass in G2, but it will significantly flare up from the quiescent, the baseline luminosity. I guess different models will produce different luminosities, and that would be one way that to test accretion disk physics, how much it would actually flare up. At the moment, there's no evidence of it flaring, even though it's past periaps, but we're still looking.
So I'm going to start with a comment, which is, for me, my takeaway is thinking about these red giants being gone by being sort of Swiss cheese, drilled out by stellar mass, or these maybe even intermediate mass black holes moving through them. It seems like you could do a simple calculation. This is the professor of thermal physics class thinking about it right now for my students. Thinking about cross-sectional, so straightforward cross-sectional area arguments to sort of set constraints. You know what the overall stellar population is, so you know what you're missing. You're missing a certain number of red giants, and if you're basically saying that's your known, your unknown is what the population of black holes orbiting through and clearing up by. And I haven't looked at the dynamics of this. I don't know if probably one event gets rid of the red giant, then my simple picture of the Swiss cheese firing, the black holes through an outer portion of the red giant, taking away a lot of it. But it must be done, right? So someone's done this and said this is an ostensible quick model of how many stellar mass black holes might be orbiting around in there. And can you speak to that and whether it makes sense with what we think of in terms of the accretion rate of building up this 3 to 4 million solar mass larger black hole, the supermassive black hole in the center?
Yeah, so that's a very good question, and people have done this, and it's a problem. So when you do simulations of stellar mass black holes plunging through red giants, they find is you need on the order of 10 of these dynamical interactions to really wipe out the red giant. And if you put that back then into the galactic center and see how many red giants are we missing, turns out you would need far too many stellar mass black holes within a certain radius. And we have constraints on how much mass you have within different radii. And you just need way too many to explain the observations. Now, it's not to say this isn't happening. I would say that very many red giants suffer these collisions with stellar mass black holes, but it won't wipe out the entire population. So that it doesn't perfectly explain the observations yet.
And you answered my unasked question, which is, I sort of stated it, which was, is it one event that sort of destroys the the red giant and hearing that it's about 10 events means really these stars are getting peppered by interactions with black holes eating away their mass.
The black holes are so small in relation to the red giants that it's like a bullet just passing straight through. So you need very many to actually, you know, for the star not to be able to just recover and be a red giant still.
Very good, thank you.
Yeah, well, what bothers me about that whole idea is that you had to come up with a whole population of things that we have absolutely no observational evidence actually exists near the galactic center. Because if there were a bunch of stellar mass black holes, they'd be flaring when they're eating things. And we don't see those kind of flares in X-rays or gamma rays.
That's true. We don't have the observational evidence for this population of stellar mass black holes, but it would be very odd not to have any.
Well, I'm sure there's a few because, you know,
there's a million
galaxies as a whole. But, you know, we see those. They shine very brightly in the heavens every time any gas is near them. So you've got to have isolated black holes that don't, somehow are not eating, except then they're somehow going through red giants and not eating and making X-ray flares. That's very hard to fathom how that could happen.
I agree. It doesn't work as an idea. But I do think there should be very many stellar mass black holes just based on IMF arguments. If you have a cluster of stars, there's going to be some proportion that are stellar mass black holes. So I would expect there's someone there. We know we have a magnetar, so there are neutron stars there. But no, you would need too many for this mechanism to work in any case. So it doesn't explain it.
Yes.
Hi. Do you have an estimate of the amount of dark matter, the distribution of that around the galactic center, and does that have any effect on your theories?
So I know theoretically there should be very little dark matter in this 1 parsec cubed. And I think all of the mass at that radius can be explained from the mass of the black hole and the mass in stars. So in terms of a mass budget and the effect it could have, I think it's very small. Yeah.
Thank
you.
Kind of a follow-up question.
In the back seat.
Yeah, where you had that object which is running away from the black hole and then all that matter streaming from it back into the black hole. What's going to happen with that? Is it all going to get sucked into the black hole? And what's going to happen with the leading edge? Is it going to get separated and wind up with a part that's going to be free, that's going to be in orbit, or is it all going to get sucked in?
It's a very good question. Personally, I'm not sure. It really depends what it is. If it is a gas cloud, you would expect it to, shocks and different interactions will heat it up, and as it radiates away, it will lose energy, circularize, become an accretion disk. You would expect most of it to end up in the black hole. But it's really not clear, and I guess what it does will really help constrain how matter actually accretes onto black holes. But it's pretty open right now.
Yeah.
Kind of a follow-up question to Professor Stevenson's question. Talking about differences in tidal disruption radii between compacts for smaller stars and for red giant stars with a much larger envelope. What sort of physical difference are you talking about in tidal disruption radius between a compact star and a swollen red giant star?
You've put me on the spot. No, I'm not going to do it on a blackboard. I'm not totally sure. I'll have to look that up, exactly what that physical radii difference actually is.
The questions you've been asking about sort of feeding back into the population of stars you're missing, and you think you don't see perhaps it's a preferential size which gets stripped away on sort of little subpopulations.
Yeah. No, that is a good idea for sure. There's also, I don't want to get into too many details, but it also seems that there's an absence of the most massive stars, the Owen-Wolfram stars. Maybe that's something to do with the fact that they're actually much more extended in size, just like the red giants. So that could direct our ideas on that. But the exact physical scale, I'm not sure.
Fun? Yes?
Yes. You were talking earlier about how there are these irregular orbits that happen in Earth. Could there be collisions that propel the larger ones, since they're actually goes like into the massive black hole.
So your question is, could the massive stars be colliding?
Yeah, and maybe like creating sort of a projection, you know, a little more towards the black hole enough for them to get engulfed, or I don't know.
So I think if you're colliding two stars, I don't think their orbits are going to change much during that collision.
Okay.
But if you do make an object more massive, there is a dynamical effect called mass segregation, which means that most massive objects will want to sink towards the center of the potential. So in that respect, when you're combining masses together, the most massive object will actually sink closer to the black hole. So that happens for sure. One of the ideas for G2 is that it was created, this gas cloud, it's created from colliding stellar winds. And in that case, you would expect it to be put on a very radial or eccentric orbit, which we see it's on, because you're cancelling out angular momentum of winds. But for stars, yeah, it would be difficult to change the orbits dramatically just because of the collision.
Oh, go ahead, Matt.
How does the cluster of stars found near the center compare to other clusters of stars found near other black holes? And also,
yeah.
really quick question: is it one black hole per galaxy? How does that work?
You mean a supermassive black hole? One supermassive black hole per galaxy? Yeah, no, that's a very good question. We don't know. In our own galaxy, sorry to answer the other one, the last one first. In our own galaxy, we're fairly sure there's just one supermassive black hole. If you had another one nearby, it would make this supermassive black hole that we do see move a lot. So we have some constraints in the fact that it's not moving much. We have some constraints on what the mass of, say, an intermediate mass black hole nearby could be. So they're quite strict. So in our galaxy, for sure, there's one supermassive black hole in the central parsec cubed. I don't want to declare that throughout the whole galaxy. But when galaxies merge, and they do merge, if they each have a supermassive black hole in the center, given enough time, they will find each other, sink towards the center of the potential, and there will be a long time scale over which you would expect to observe two, or maybe even more, if more galaxies are merging. So people are looking for these, the signs of these things. And for sure, in merging galaxies, you can see two distinctive, if they're active, you can see active galactic nuclei, you see two, so you know there's two black holes in that merger product. But it's actually a huge field of study, how they find each other, how they eventually merge. Can we catch ones that are just in their act? Because that would be really interesting. Yeah. And as for the nuclear star cluster at the center, how it compares, it's much more dense, much more dense. And it's got a huge range in age in the stellar population. So you have really old stars, and you've got stars that are 200 million years old. You've got stars that may be 100 million years old. And now this recent starburst that's about 4 million years old. Whereas a lot of other star clusters seem to be very much like one or two bursts of star formation, and they're done because all the gas escapes. But I guess it's harder for things to escape in the center of the galaxy, so you can build it up again.
Yes.
Would it be possible to
Oh,
have a
sorry,
binary
Steve, no.
black hole, like in orbit about each other?
I'm sorry.
Would it be possible to have like a binary black hole where they would be the two of them in orbit about each other?
Absolutely, yeah.
You have a center of the galaxy?
So we know observationally that that's not happening in the center of our galaxy, but we do expect that to be happening in other galaxies, particularly ones that have merged. Yeah.
There's at least 3 or maybe even more by now that have been well documented of double supermassive black holes from merged galaxies.
Yeah, in other galaxies, we've definitely seen multiple cases of at least two orbiting each other. Here?
Yeah, regarding that great simulation you showed of the young stars and an orbital disk around the black hole, did I read that correctly in that there's projected orbits from 1893 to the present to make that movie?
So obviously we were not looking in 1893.
How did they do that?
That's simply for visual effect to show what it would look like from 1893 all the way up until present. I think that was the G2 movie. So G2 was discovered in 2012. Now they have observations that they could go back and see where it was for the past, I think, 10 years. And from that, reconstruct its orbit. And from that, you're able to go back, as long as you know its orbit, you're able to go back much further just for visual effect.
You go back over 100 years and have an accurate description of the orbits?
That's a very good point. If it's a gas cloud, it's not just like a star that stays on roughly the same orbit for a long time. It would feel drag forces from this X-ray emitting gas around the black hole. So yeah, that's something I'm actually looking at the moment. From the change in its orbit, we assume it's going to be changing its orbit soon, can you say something about the density of the gas around the black hole from the drag forces? You would not, as you say, expect it to be on the same orbit. Yeah.
Well, let's thank our speaker again.